Assalamu alaikum everyone. Welcome to another tutorial of electrical measurements. First, if we'll go through the contents of this chapter, I have already provided you with the links of PMMC type of instruments and induction type of instruments, and the topic galvanometers and mathematical theory of D'Arsnoval galvanometer, and this was your assignment. So we are left only with electrostatic type of instruments and dynamometer type of instruments. Today we will be starting with electrostatic type of instruments. What happens in electrostatic type of instruments is that, as the name suggests, it works on the electrostatic principle. Here, these type of instruments work on the attraction or repulsion between the electrodes. If the electrodes will be of a similar charge, they will repel each other, and if they will have opposite charge, then they will attract each other. This is the main objective. This is the main principle that is used in these instruments. After that, when this attraction or repulsion, this is actually force. So what happens, we want to produce force. So force is produced by means of attraction or repulsion, and that force, or we can also say as torque, that torque is used to deflect the pointer. Now, what happens in electrostatic instruments is that the deflecting torque is produced by the electric field on charged conductors. So, if we all know, when we separate two charge plates by some dielectric medium or air, that forms a parallel plate capacitor. So, in a way, we can say that these electrostatic type of instruments are actually parallel plate variable capacitors. And these electrostatic instruments can be used as ammeters, voltmeters, wattmeters, but they are majorly used for the measurement of high voltages. Now, if you look into the figure, what I have shown is that there are two ways by which we can provide this attraction force or repulsion force, or the arrangement of parallel plate capacitors. In first, we have just placed two electrodes opposite to each other, in which one is fixed and another is movable. Here, this configuration forms the linear configuration of electrostatic instruments. Another configuration where I have shown these triangles sort of things, triangular plates, these are actually the movable discs. That means here the discs move in rotatory motion, while in linear instruments there is linear motion between the plates. Here in rotatory motion, the rotational torque will be provided, while as in case of linear instruments, linear force will be provided. Now let us see how the force will act in these two cases. First, let us consider the case where we have just placed two parallel plate capacitors, where one plate is fixed and another plate is movable, and on movable plate we have attached a spring to provide the controlling torque. Hence, the torque provided here will be due to the spring. Controlling torque will be provided due to the spring. What happens in this case is that here obviously one plate is positively charged and another plate is negatively charged. What will happen is that the movable plate will try to move towards fixed plate. Hence, due to the force of attraction. Hence, this force of attraction we know was due to the electrostatic charges, and therefore we can say that this force is known as the electrostatic force of attraction. Here, the motion was linear. As we can see, the motion is linear here. In another configuration I have shown is we have used two plates. Here the lower plate is fixed while the upper plate is movable, and here also spring control is provided. Here also, due to the attraction or repulsion, the plate will try to move towards the another plate, but here the motion will not at all be linear. You can also see from the previous figure where I had shown those two triangles. The motion here will be rotational motion. That means in linear motion we can use the term force and displacement to represent the linear motion, while as in case of rotation motion we can use the terms torque and angular displacement in terms of force and linear displacement. What happened in both the cases was that the force was produced due to the electrostatic charges, we can say that this mechanism resembles to that of a variable capacitor, and we all know that capacitor stores the energy. So we can say that the force or torque is due to the fact that the mechanism tends to move the electrodes to the position where the energy is stored maximum. What is required here is the maximum energy. Now coming to another subtopic, that is force and torque equation in electrostatic instruments. This torque equation was important in all the instruments, whether it be PMMC instruments, induction type of instruments. This is very important, torque equation, because it is this torque equation which will help us to determine how the deflection of pointer will take place. And we have already learned that this force is produced until the maximum energy is stored, and we all know that motion is either linear or rotational. So the force produced will be due to the linear motion or rotational motion. Then we will first consider the case of linear motion. After that we will consider the case of rotational motion. Now coming to the first case, that is linear motion. As you can see in the figure here, two parallel placed capacitors are shown and some voltage is provided between the two. We all know when voltage is applied to any capacitor, the capacitor stores that energy. And what is the formula for energy stored by a capacitor? It is half of CV square, where C represents the capacitance and V represents the applied voltage. Now see, if we will increase voltage by slightest amount, obviously capacitor energy stored in a capacitor is directly proportional to the square of voltage. If voltage will be increased by some amount, definitely there will be an increase in the energy stored. So we can write that formula for current is charge upon time. We can write I is equal to dq upon dt. In place of charge, we can write q is equal to cv. That's the formula for q. After that, we will differentiate c and v with respect to time. Here, what we have done, we have just simply applied the uv formula, the product rule of differentiation. U derivative of uv is equal to u derivative of v plus v derivative of u. Hence, what we will get current is equal to c dv by dt plus v dc by dc. Here, c is also variable and v is also variable. After that, if we will see what our input energy was, input energy was electrical energy, and electrical energy is represented by the formula V I dt. Here we have represented time by dt. So in place of V, we can simply write V. In place of dt, we have wrote dt, and in place of I, we have written that what we derived already, c dv upon dt plus v dc upon dt. What we will ultimately get is that input energy is vc dv plus v square times dc. Now, if we want to see the change in the stored energy, the change in the stored energy will be when we will change the capacitance by some amount, when we will change the voltage by some amount, the capacitance will change. So the change will be the difference of the two, and on solving that, what we have actually got, the change in the stored energy is half of dc v square plus cv dv. You can derive it on your respective notebooks. This is ultimately what we will get by neglecting the higher order terms. Now, by the principle of conservation of energy, we all know that input energy is always equal to the output energy. Here, in this case, our input energy was the electrical energy. And what is the output energy in this case? Here, first, capacitor stores the energy. That is, we can say that's the output energy. And also, some energy is utilized in moving the movable plate of the capacitor. So we can say that input electrical energy is equal to increase in stored energy plus mechanical work done. Hence, we will substitute the required values of input electrical energy, increase in stored energy, and mechanical work done. we all know that work is equal to force into displacement. The force here is linear, hence we can write F, and the displacement due to a small change in this voltage dV is dx, small change in displacement due to small change in voltage. So the mechanical work done will be F dx. On equating the two terms, we will ultimately get the equation F is equal to half of V square C dC upon dx. That is, force is equal to half of V square and differential of capacitance with respect to displacement. This was the case with the linear motion. Now if we will see what will happen in rotational motion, we will simply replace force by torque. Velocity will remain unchanged. This voltage will remain unchanged, but linear displacement will be changed by angular displacement theta. Hence, in rotational motion, the formula that we will get for the deflecting torque is half of V square dC upon d theta. Now, in order to get the deflection, what we do is we consider the equilibrium point where controlling torque is equal to the deflecting torque. Hence, we will equate the two. Controlling torque here was produced due to the spring control. Hence, we can write K theta, where K is the spring constant. On equating the two, what we will get the theta equals half of V square upon K dC upon d theta. Here, as you can see from this formula, here theta varies with the square of voltage. So definitely this follows the square law response. So the scale will not be uniform in this case. This is very important point, that the scale will not be uniform. Now coming to the advantages and disadvantages of these electrostatic instruments. First, advantages. These instruments draw negligible power from the mains. If you will consider the case of DC or AC, now since we learned that it varies with the square of voltage, so it's obvious that it can be used both for AC applications as well as DC applications. Here in case of DC, the initial current is 0, but in case of AC there is slight charging current, but that too dies with time. So we can say that the main advantage of these instruments is that they have low power requirements. Another that is, it can be used both for AC and DC. Here deflection is directly proportional to the square of voltage, so there will be no frequency errors, no waveform errors, no hysteresis. Here there will be no errors due to the stray magnetic fields, since the instrument works on electrostatic principle. The main advantage is that these are used for very high voltages. Now coming to the disadvantages. The disadvantage is that their applications are specific, especially in case of AC circuits. For limiting the high currents due to short circuit, a protective resistor is used in series with it. Another disadvantage is that these are expensive, these are large in size, and these are not robust in construction, and they don't have a uniform scale, and their operating forces are small. Now, as I have already provided you with the PDF of this book, whether it be PMMC instruments or induction type of instruments or galvanometers, numericals are important here. So I have just shown one numerical here, but you should try all the numericals that are shown in your book. Here, what we are given an electrostatic voltmeter reading up to 2000 volt, and it has spring control with some torsional constant is given. This is spring constant is given, and it has a full scale deflection of 90 degree. That means here deflection is given. Here the deflection is given in degrees. We have to convert it into radians. The capacitance at 0 voltage is 15 picofarad. What is the capacitance when the pointer indicates 2000 volts? We will use the formula half of theta is equal to half of V square by K dC upon d theta to calculate the rate of change of capacitance. and we will ultimately get the required value by putting the values there. Similarly, you should try out the numericals that are given in your book. Well, that was all for today. Thank you and stay connected.